Hello, Assalamualaikum warahmatullahi wabarakatuh. We are from Group G and our project title is Hydration Prediction System using Artificial Neural Network. First, I will introduce our group members. So, my name is Abdul Nawfal Fitri bin Abdul Ghani, and next we have Muhammad Nabi Ikhwan bin Muhammad Marzuki, and we also have Muhammad Iman Imran bin Muhammad Rusman, Nurul Ali Fahmi bin Muhammad Azim, and lastly we have Mikael Johan bin Jafri Johan. So I will tell about the abstract of our project. So our project is a dehydration prediction model and was developed using a multi-layer perceptron neural network, combining hydration awareness data with clinical urinalysis data, and also pre-processing steps included feature encoding for categorical variables and z-score normalization using standard scalar, and this is to ensure the data consistency. The multi-layer perceptron architecture features 3 hidden layers designed to capture complex patterns within the dataset. The model demonstrates accurate pattern learning, enabling reliable dehydration prediction to support early health risk identification and intervention. So, why are we doing this project? This is because dehydration is a silent health risk. It affects cognitive performance, physical endurance, and organ functions. Traditional hydration assessment relies on invasive clinical tests or equipments, blood osmolality, urine specific gravity, and else. So the problem is not accessible real-time non-invasive method exists for everyday hydration monitoring. So our solution is to develop an artificial neural network based prediction system that combines behavioral data and also urinalysis indicators. So our objective for the project is to classify hydration status, either hydrated or dehydrated, using a trained multi-layer perceptron model. So the significance is it will enables early dehydration detection without requiring laboratory equipment or medical expertise. So why early detection matters? Dehydration impairs physical and cognitive functions, like I said before, and timely identification helps prevent fatigue, headaches, and serious health complications. So by doing the multi-layer perceptron approach, it will capture this project will capture complex data interactions, enabling accurate dehydration prediction through robust preprocessing and also pattern learning.
For installation on Python, to build our hydration predict system powered by a deep learning model, the very first and the most critical step is setting is a stable development environment. We selected Python 3.11 or higher as our foundation programming language. We choose Python because it's a massive ecosystem for artificial intelligence and a seamless compatibility with Windows platform. Our software architecture relies a specific set of 5 internal libraries that work together. For the first one, it TensorFlow and Keras. They serve our primary framework to construct, compile, and train our multi-layer perceptron MLP neural network. For the second one, in Pandas, this our data entry gateway allow us to read the raw CSV file for the hydration, awareness, and urinalysis dataset into the structured data frame. The third one is a NumPy. This work behind the scene to execute the high-speed vector operation and ensure experimental reproduction by seeding our random number. For the fourth one is the skittle. This is integrate strictly for pre-processing tasks. For the last one is Tikita. This is a Python native GUI toolkit for Windows. For the Windows setup, we made sure to check the add Python X to pass during the installing. After that, all dependency were easy done via the single pip command in the command prompt. That's for the installing on the Python. Moving on, let's talk about deep learning is the backbone of this system. Deep learning is a specialist subfield of AI that mimic that biology structure of the human brain to process data and discover complex. relationship. Unlike the conventional machine learning algorithm that require manual feature engineering, our neural network pass input through subsurface layer of interconnect neuron to build a deep hierarchy of feature automatic. Inside our artificial neural network, data processing is handled through mathematical operation of vector. For a single neuron, the output z is calculated as a linear combination of the weight multiplied by the input theta. The input x represent use attribute like a water intake, urination frequency, and the urine color score. We implement a skewered architecture for Keras where data flow precise in one direction. We start three fully connection hidden layer with a dense configuration of 3 to 90 and 8 neuron reflective. Lastly, the model is compiled using the ADAM optimized to achieve highly stable and adaptive weight update. During the training, we use binary cross entropy loss as our mathematical objective function to evaluate error across 50 training outputs. By correctly configuring our Python environment and deeply understanding deep learning and mechanic, our model achieve fantastic training stability. Thank you very much.
Assalamualaikum and hi everyone. I am Iman Imran. To start things off, I want to show you how we got our data and how we clean it up before doing any math. Basically, we have two data set. One is hydration awareness data set, another one is urinalysis test data set, which both are from Kaggle. Let's look on the first one. Hydration awareness data set, which comes from a lifestyle tracking study. It has 5,000 rows of daily logs showing how much water people drink, how is the weather outside, how active they are, and if they have symptoms like headache or fatigue throughout the study. This main file includes all the baseline details found in dataset 1 as well. Next, our second one is urinalysis test, which comes from a local clinic in Philippines. The dataset consists of around 1.5k real patient urine tests. This one gives a deeper look into the actual signs like urine color, pH level, specific gravity, and whether the lab found any bacteria or white blood cell inside the urine itself. It's an expanded version of the basic info in dataset 2.
Okay, next, let's look at our flowchart to understand the system, how the system runs. The program begins by reading the dataset, handling nulls, value, and mapping urine color to medical risk score ranging from 0.02 to 0.90. It defines the target level, requiring a user to drink at least 8 cups of water and urinate at least 5 times to be considered hydrated. And normalize that features to train the sequential model using the ADAM optimizer. Once trained, the system launches the Tkinter interface where the user can input their current daily statistics such as water intake, activity level, and urine color. These input are scaled and fed into the train A and N, which calculate a probability score. If the score is 0.5 or higher, the interface output well hydrated status. But if it falls below 0.5, it immediately alert the user that they are dehydrated. Okay. For our project, we follow the CRISP DM learning process to predict human hydration level using an artificial neural network. We start by collecting our raw data, which include a 5,000 record hydration awareness dataset and a 1,436 record urinalysis dataset. During the data preparation phase, we merged urine color score, engineered our target label, encoded categorical data, and apply a standard scalar before splitting the data set 80 to 20 for training and testing.
For our model, we built a multi-layer perceptron with 3 hidden layers and a 20% dropout rate, carefully evaluating its training and validation accuracy over 50 epochs using binary concentrophy loss. Finally, we deploy this trained model into a Tkinter GUI to provide user with a real-time hydration risk percentage and actionable action. Okay.
Now, let's look at feature selection. Before building any models, we had to look closely at our column to decide which variables are actually add value to the model and which one are just extra noise. Here is exactly what stayed and what was removed from both files. For dataset 1, remaining features only water intake liters, weather condition, physical activity level, urination frequency, fatigue level, and headache reported. While liters are great for scientific calculation, they can a bit abstract for a general audience to visualize it in everyday life. To make our finding much more readable and easier to understand, we converted our water intake metric from liters into standard household glasses. Moving over to the urinalysis test dataset, which is dataset 2, the remaining features only age, gender, and color. The removed part, we remove transparency, pH level, specific gravity, bacteria, white blood cell, protein, glucose, and many more. Now, we already know exactly what features we state. I want to take a moment to explain the logic behind why we keep it. We didn't just pick them at random. Every single column that state has a specific job to do in our predictive model. Let's look at our hydration awareness dataset features first. We kept water intake liters, or now we call it as water intake in glass, because it is our absolute core metric for baseline fluid consumption. Next, we have weather condition and physical activity level. We state them because they are the primary external force that drain our body fluid. They give context to whether a person's intake is actually enough for their environment. Next, we also have urination frequency, which is an agreeable feature because it acts as direct biological output tracker. And the last one, we have fatigue level and headache reported. These two give us immediate and real-world symptoms of how hydration happens in daily basis. Let's move on to the urinalysis dataset. We only have three features here. First, we have age and gender. We state them because health benchmark change drastically across different demographic groups. So, they provide an essential baseline of our data. Second, color state because it is a vital physical property. It is immediate visual cue as Dr. sees as we prove in our analysis, it directly aligns with the body's actual hydration concentration.
Assalamualaikum and hello everyone. I am Mikael Johan and now we will be talking about the data analysis. So for our data preparation and hydration patterns, we start with data preparation and cleaning, which we remove null missing values and duplicate entries from both datasets. Label encoding applied to convert categorical variables into numerical form. And then we use the standard scalar, which is Z-score normalization apply to stabilize features range. Then we merged both the dataset, which is the dataset 1 hydration awareness and dataset 2 urinalysis on participant ID. Next, for the hydration awareness behavior and behavioral pattern, low daily water intakes strongly correlates with dehydration symptoms. Physical activity level directly impacts hydration demands and loss rates. Self-reported awareness often contradicts actual clinical hydration status. Frequency of water consumption is a stronger predictor than total volume. Next, for the clinical urinalysis trends, higher urine specific gravity indicates concentrated urine, which means the dehydration. Urine color index serves as a visual biomarker for hydration level. pH level shift under dehydration condition due to metabolic changes. Combined clinical plus behavioral feature yields better prediction than either alone. Next, let's move on to our results. The hydration prediction system demonstrates a strong performance by integrating behavioral and physiological data. The MLP model trained effectively, achieving a good generalization on test data with minimal overfitting across both hydration awareness and clinical urinalysis dataset. Next, we will move on to our project demonstration. Hello everyone. So this is our project demonstration. This is our project. I would personally would prefer to use it in a small kind of window. So first of all, would want to show you. So this is what will happen after we run the program. It will show that we load the data set, and then we did the training, and this would be the output with the tick enter is the output. So first of all, it will show that our accuracy is around 99.6%, and this is our sample, which is 5,000 to plus 1,425. I would also like to show that it also show that our train and test split is 80 to 20, which we mean 4,000 for training and 1,000 for testing. So next is we can choose on how many cups do we drink today, which will be, let's say I drank like 8 cups I think today, which is a good amount actually. And then for my urination frequency, I would say like maybe I urinate for like 4 times today, and I would say that my self-focus rating today is around 4, and the urine color maybe like light, maybe a yellow or light yellow maybe. Then the current weather, the Malaysia is very hot today. It's gonna, so I just gonna put hot. And my physical activity I will put as medium, as I don't really do any heavy physical activity today. My fatigue level is, I would say I feel a bit tired, with all the assignments and all the group project. Is headache present? No, I do not have a headache, So we will analyze the hydration status. We will say that I am dehydrated. I am 100% dehydrated. From the train and the data set, this is the results, the prediction. Okay, so that's all I think.
In conclusion, our project have developed a robust dehydration prediction system using MLP artificial neural network, combining behavioral and clinical data sources for enhanced model accuracy. And also we have a feature encoding and z-score normalization via standard scalar were critical to model stability, performance, and accurate pattern recognition. We also have successfully developed with a user-friendly GUI, enabling real-time hydration status monitoring and health recommendations. So that's all from us. Thank you.